Welcome to the Here's a Summer of Programming Languages. Have you ever asked yourself, am I using a suitable programming language for this task? Then this collection of introductions to programming languages used in research software engineering has something for you.
Hey, I'm Damian Rouson, Senior Scientist and Group Lead for the Computer Languages and Systems Software Group at Berkeley Lab. I was asked to talk to you about Fortran, when and why to use it. I'll focus on modern Fortran, the latest version of which is Fortran 2023, and I'll cover when, how, and why we use it on the Berkeley Lab Fortran team. Many of the packages that I'll talk about today have a broad list of contributors. I'm showing only those with whom I've worked with most closely. The Fortran Package Manager, for example, has over 40 contributors worldwide. The LLVM Flang compiler infrastructure project has hundreds, if not thousands, of contributors. I'll talk about motivation in terms of why Fortran matters, but also I'm going to use a slide from a talk that I gave last year to a group of nuclear physics researchers who I had heard were many of whom were starting to move away from the Fortran programming language. So the title of that talk was The Problem is Not Fortran. I'll also cover open source software to which my group contributes across domains from software building to deep learning, computational science, correctness checking such as unit tests and assertions, parallel programming, and I'll conclude with a summary of when, how, and why we use the language. I oftentimes say Fortran matters most in fields that embraced computing early. That includes weather and climate, for example. Every time you look at a weather forecast, you're looking at the results of a Fortran code. Over 190 nations have signed climate agreements based on observations and the results of Fortran codes. The Nuclear Regulatory Commission licenses nuclear power plant designs based primarily on the results of Fortran codes. NASA develops Fortran simulation software that's also used in industry by companies like SpaceX. So, the problems I see as many people think about Fortran is not so much with the language itself, but there are some problems, and those are related to perception. Most of non Fortran programmers know only of Fortran 77 to 90, versions that are 35 to 48 years old. There are some issues with compilers. I devote a significant fraction of my time to submitting almost a bug report a week and have since the beginning of 2024. There are some problems with the state of the practice in Fortran. Most Fortran programmers know Fortran 90 to 2003, versions that are 22 to 35 years old. The solution I see to perception is to look at data. If you look at the TIOBE index that measures the popularity of programming languages, Fortran peaked back around 1990 at the second most popular language. There was then a steady decline all the way to 2020, where Fortran bottomed out at about 31 in terms of programming language popularity. But there's been a significant resurgence. And I've noticed that over roughly the past year and a half, Fortran has averaged around 10th on the list of programming languages. And I'd say that's largely because there's a group of programmers across all age ranges, by the way, who are actually very excited about what's happening in Fortran and developing a lot of great open source software, oftentimes in new domains with which you probably don't associate Fortran. In terms of compilers, there are new compilers coming out with a lot of exciting features. I'll mention the Fortran compiler that can be used as an interpreter, much like the experience of using Python or MATLAB. My group contributes unit tests and runtime library support for the LLVM Flang compiler, the next version of which, 21, will have a lot of exciting features, including the ability to automatically parallelize loops using Fortran's do concurrent construct, which LLVM Flang 21, thanks to a collaboration with AMD, will be able to automatically parallelize on CPUs. And I look forward to future versions of Flang, which like some other compilers, the HPE Cray compiler, NVIDIA, for example, and Intel that can also offload automatically do concurrent to GPUs. Another exciting feature set, multi-image execution. My group is working on that with the French company SciPearl. This enables you to adopt a single program, multiple data, SPMD parallel programming style, much like people often use with the message passing interface, MPI, to write code that can work in shared or distributed memory, can run on as many as 100,000 cores on a supercomputer, just writing Fortran. You can do all of this without MPI anywhere in the source code, without OpenMP, OpenACC, CUDA, the tools that are oftentimes used for loop level parallelism. And all of this was launched on largely DOE funding through a worldwide private-public collaboration. The solution I see to the state of the practice for Fortran is to take advantage of novel idioms, paradigms, patterns for writing code in software that comprises a Fortran 2023 ecosystem. And we'll talk about some of those packages like the Fortran Package Manager, one that is in a domain, again, where you wouldn't expect to see Fortran. Fortran Package Manager was developed originally by my colleague Brad Richardson, who originally developed it in Haskell. I remember watching this grow like wildfire, where a number of Fortran programmers decided they were so excited about it that they rewrote it in Fortran in order to be able to contribute. And so the Fortran Package Manager itself is written in Fortran. And when you develop in the language of the users, you lower a barrier to user contributions to your code. Within a year, there were 18 developers worldwide. Now there are over 40. And FPM automates building your software in a way that I'll compare to Make, for example. If you're writing Make files, where you specify your source files, as well as the interdependencies within your project across files. You could also think about a higher level of automation with the cross-platform Makefile generator, CMake, that can generate a project for you of Makefiles, or say the Ninja system for building software in parallel. With CMake, you specify your source files if you're using best practices, but CMake will discover the dependencies between those source files for you. FPM gets you to an even higher level of automation, where not only do you not need to specify the source files and the dependencies, you only optionally specify subdirectories where those source files reside. In fact, if you use the set of default directories that FPM expects, putting your main programs in an app directory and any files that you'd like to build into a library against which you'll link the main program into a source directory, your tests and a test directory, examples and example directory. If you do all of those things, you don't even have to specify where the files are located. FPM discovers the source files and discovers the interdependencies between the source files and your project. And better yet, if you have external dependencies, and if those are also FPM projects, then acting like a package manager, FPM will go out and download those, build them, and link your program to them. This 4-line file, called an FPM manifest, it's an fpm.toml file. TOML stands for Tom's Markup Language. In fact, 3 lines if you subtract the one blank line there, is the entire build system for fiats, the deep learning library that we develop at Berkeley Lab. Fiats expands to functional inference and training for surrogates, because we use it to train surrogate neural networks that substitute for physics components of computational science models. Or you can expand the name to Fortran inference and training for science. So FPM simplifies software building for some of the most common workflows that involve Fortran, and by the way, C and C++. For example, SuperLU is a linear algebra package, also developed at Berkeley Lab, to which I contributed a 3-line FPM manifest. That plus one new soft link is able to build 32,000 lines of C code. This is just showing an example of how you might get started with FPM. There's an fpm new command you can use to create a new repository. This is showing you the directory structure that gets created with the app directory containing your main program, the source directory containing a file that gets built into a library. And you can use the fpm run command, for example, to run your program, and fpm test to run your tests. It's that simple. This is the fiats repository, where you can see that fiats is 99% Fortran. There are a number of benefits you get from having a solution that's all Fortran all the way down. For example, we export functions that are almost all pure functions. Pure is an attribute that gives the Fortran compiler the ability to check that your procedure doesn't have certain side effects, such as input and output. Writing pure procedures enables certain optimizations, including parallelization. In fact, if you want to invoke a procedure inside a do concurrent construct, according to the Fortran standard, that procedure has to be pure. This is something that would be much harder to achieve with an API that, for example, wraps a C++ library, such as libtorch, in which case, not only will the compiler not only be able to verify which procedures are pure and take advantage of some of the optimizations that affords, but there's also additional complications associated with language interoperability. For example, one package that wraps libtorch has 30 functions just for converting Fortran pointers to C++ pointers, and another 30 functions for doing the reverse conversion. So that's 60 functions that vanish from your interface just by having an all Fortran solution all the way down. Let's take a look at what that buys you. In most scientific programming, whether you're in Fortran, C, C++, Python, or another language, we write a lot of loops. Loops are a 60-year-old technology. There were loops in Fortran 66. Loops are also inherently serial. They have to be, because it's sometimes important for you to be able to ensure that one iteration happens before another. Think, for example, if you're doing something like time advancement of a differential equation. So what we do is we then write these nested loops. Here I'm invoking an inference procedure on a neural network object, and I'm passing in various elements of a 3D array of inputs objects, inputs tensors. And after I do that, I come back and say to the compiler, oops, I don't really want you to do this sequentially. I want you to do it in parallel. And I do that with the OpenMP directive at line 129. And I say, I didn't really need to nest these. I want you to collapse these into one loop. Many times people ask questions like, how do I parallelize this algorithm? I like to flip that on its head and ask, why would you ever serialize that algorithm? Why not just write a parallel loop to begin with that communicates to the compiler that you can do all of these iterations in any order, including in parallel? That's what you're doing with do concurrent. Or better yet, Fortran enables you with its many array features to do things like declare a procedure to be elemental, which is what we're doing here at line 74. We're taking advantage of the fact that the infer procedure in fiats is elemental. And what that does is it tells the compiler, if I write this procedure just as if it takes scalar arguments, I still want to be able to pass in an array. And that array could be anything from a one-dimensional vector to a two-dimensional matrix, all the way out to a 15-dimensional entity. And the compiler will simply apply that function to each element of the array and give me an array result back. I'd like to work towards a world where line 74 can be automatically parallelized on its own, or at least if I surround it with a couple of OpenMP directives. That's where I see things headed. This is what that buys you. You get essentially the same performance as you see comparing the red and the green line between automatically parallelizing do concurrent versus writing OpenMP compiler directives yourself. And this is running on Berkeley Labs' Perlmutter supercomputer. The Fortran ecosystem that I'm talking about involves a software stack that has both an application such as Matcha, which we also develop at Berkeley Lab. It's studying the motility analysis of T cell histories and activation, where we're simulating the random walk of T cells through human tissue, but also the diffusion through a three-dimensional partial differential equation for diffusion, essentially the heat equation, of species that the T cells emit. We're also using Julienne, a unit testing and assertions package that we develop, also written in Fortran, to write our test suite, and then working towards being able to have the compiler support the communication and multi-image execution in Matcha by linking our code to Caffeine, a package we also develop, the Co-Array Fortran framework of efficient interfaces to network environments. So this is what it looks like when you're writing code inside Matcha. Looking at line 228, it's reminiscent of something a former colleague, Catherine Long, who's now at Texas Tech University, said to me once: software abstractions should resemble Blackboard abstractions. Here I'm writing an operator like Laplacian, where Fortran gives you the ability to define new operators, not just overload existing operators. When you do that, you bracket the operator with dots. And the idea here is that I'm expressing the time advancement of the heat equation in very much the same way I would if I were writing it on a blackboard. At line 213, I'm checking the correctness of my code, in this case to compare a more functional programming style that we get from the function that we see down below to a more traditional procedural style of programming. What's really exciting is that I'm writing out a natural language English sentence here. TF approximates TP within tolerance. That's all supported by Julienne. That's one of the idioms that Julienne provides. And TF and TP are both three-dimensional arrays, where I'm applying that expression with a scalar tolerance. And so this actually represents a lot of different checks happening across these three-dimensional arrays, and I'm collecting all of those up with an all operator that packages its result up into a test diagnosis that tells me if the test passed or failed, and gives me a diagnostic stream for output only for the elements that fail. So when, how, and why we use Fortran. It's really useful for doing math. You can go all the way back to 1957, the original Fortran manual from IBM referred to Fortran as a formula translation system. It's really useful when performance matters. You can just write Fortran to do parallel programming in distributed memory with automatic offloading to a GPU. You can use it in domains that you probably don't think of for Fortran: build systems, deep learning, correctness checking, runtime libraries for compilers. And in my work, I've done a lot of use of Fortran in software archaeology, porting, tuning, and modernizing legacy codes, ending up in a better place than oftentimes would be the case for less budget than if we translated the Fortran to a different language. So why is all this true? I think it's largely because Fortran benefits from a standards committee, and in full disclosure, I'm on the committee, that sees computational science as its target audience, sees performance as paramount, and aims for high levels of backwards compatibility, meaning that you can take oftentimes a Fortran 66 program, compile it with a Fortran 2023 compiler, and it'll work out of the box. Here are a few references to recent articles that we've published on our work with the packages that I've shown you today. Thank you.
Thank you for watching this introduction. Please check out the slides on Zenodo, linked below, and see you next time.